Hey guys, thanks a lot for sending your suggestions. I got 3 topics that I don't think I really covered at all during the year. One of them we kind of bounced off of a little bit. One of them I was saving for later and just never got to it. And the other I just left out completely. They're super short. They're just little parts of a subject, so they shouldn't be too bad. So I've got a list of things that I didn't cover. That's this PowerPoint. And then I got a list of things that you guys have requested that I go over again. And that's going to be coming probably next week. Friday, we'll probably still just have another free response problem. And I really think that's going to be super useful if you keep doing those. I'm going to try and find a good one that's representative of a lot of different units and the kinds of questions that I expect you'll see on the actual AP exam this year. So let's go through these 3 short topics. The first one is polymers, pretty straightforward. They don't ask, the reason this is not in here, and this is one that I never taught about, the reason it's not is because I've only seen one question from AP and all the tests that I have about polymers, and that one question could be answered without any education about polymers. It was a density question, so it was really simple. So you may be familiar with polymers from biology. You may remember that they are, subunits repeated over and over again. And that's all it means. Poly means many, mer means unit. Your freshman year in biology, we talked about amino acids being chained together into a polypeptide, right? So here's an amino acid, and it has a good name. There's an amine group. There's a carboxylic acid, right? An amine group and a carboxylic acid. The 2 of them are attached together doing a thing called dehydration synthesis. We're taking this water out of here to make this peptide bond. And it's just called a peptide, and a chain of amino acids, you may remember, is called a polypeptide. But we also polymerize sugars, right? This bottom diagram is glucose is chained together into starch. A polymer of nucleotides, that's what DNA or RNA are. So it's just a chain of repeating units. And the units don't have to be identical, but they should be similar. Of course, the main place this comes in chemistry is in polymers that are used to make plastics. It's a very versatile set of molecules, and it's largely because you can form these long chains, and then the long chains you can connect to each other to make a molecular mesh and make something of some strength, but it still has some pliability and things like that. So we're talking about plastics. We're talking about polypropylene, polyethylene, polyvinyl chloride. You may not recognize these names, but you have encountered these products. These 3 molecules are probably all 3 sitting in front of you right now. PVC is one it's a pretty strong one. It's pretty dense. We use it for plumbing and all kinds of things. Polyethylene is what your water bottles and stuff are made out of. So we got a lot of different compounds that we use for this. But the idea is still the same. It's a building block that gets repeated over and over again. Polyethylene is really simple. It's a couple of double bonded carbons like this. And polyvinyl chloride is basically you turn one of these guys into a chlorine, right? So there's a polyvinyl chloride monomer. And so when you start chaining these together, so you break this bond, and that leaves an electron available to bond on each of those carbons because you had them shared in that bond, in that second bond. They're now available, and we can chain together another ethylene and another ethylene and another ethylene. Propylene just means you have a methyl group on here instead of just a hydrogen. A monomer is just a single unit. A polymer is a chain of those units. So when we're looking at the basic structure of any polymer, we've got monomers, which are the individual molecules like we were just talking about with the ethylene. You chain together to make a polymer, but then from there you've got another layer of structure, and that is when these polymers start lining up side by side and you've got these intermolecular forces. Oftentimes these are just London dispersion forces, but oftentimes they do have some dipole-dipole interactions, things like that. So sometimes these molecules fold up and form these connections between each other, but even multiple chains can form connections between each other. And there's 2 big things that they ask questions about with polymers, or at least that I expect them to ask questions about. There's really only one thing I've ever seen them ask about, and that's density. But I expect that they could ask a question about the strength of the polymer, and that's going to come down to the intermolecular forces. So those that have dipole-dipole interactions are going to be a stronger plastic. And then there's also a thing called cross-linking, which is where these strands can actually form covalent bonds between each other. So this is going to be a lot stronger because a covalent bond is much, much stronger than any of those intermolecular forces we talked about before. Okay, but it's pretty straightforward stuff. There's really not anything here that is new information that you wouldn't be able to figure out. But it may make you faster at answering the question, and that is always something we want. So this is the one question that I've seen that's a polymer question. I feel like there might have been a multiple choice question somewhere, but I also feel like it was dismissively easy. But if you look at this, all it asks is, given the spacing between the polymer chains in PP and PVC, so here's PP, polypropylene, and see, you can see this is our propyl. So propyl means 3 carbons. And PVC, which is that polyvinyl chloride. So there's my ethylene. Vinyl is just an old word for ethylene. So it's a bunch of vinyls, basically a bunch of ethylenes chained together, each one having a chlorine atom on there. And so we did this little N thing that tells you, right, there can be any number of these things in there. And you can see it's here on this one as well. Any number of these things in here. That's just an indicator that this is a polymer, because it could be a whole bunch of these things. And so when you're looking at this question, the spacing between the chains is similar, okay? The beads that sink are made of which polymers? The spacing in between is going to be something that affects the density, because space in between, empty space, means less dense. But in this case, they tell us that the spacing is similar, which is going to be the one that sinks, so which is the one that's more dense, and just which one has more heavier atoms. If you look at a single monomer, you can see, right, I've got some hydrogens, and then I've got this methyl group. And I've got the same thing over here, only I've got a chlorine. Now, what's the chlorine's weight versus a methyl group's weight? Carbon's 12, hydrogen's 3, so that's about 15. And chlorine is 35.45, so that's a lot bigger than 15. So that means that this one is more dense because it has more mass in roughly the same amount of space, because it says the spacing is similar. So I don't know that you really even need to know about polymers to answer that question. That seems pretty straightforward. Mass over volume. That's a density question. I went ahead and stuck the second part of this question on here. Even though it's not really a polymer question, it is talking about the monomers and the intermolecular forces. Now it says the boiling point of this guy is lower than this guy, and you have to explain that. And it's easy enough to answer with just London dispersion forces, because this guy's got a lot more electrons involved, so that means more pushing around for those London dispersion forces. But we're also actually going to get a dipole-dipole interaction between this chloride, because this is a polar bond. That bond is polar. So this is going to have that little delta minus, and this carbon is going to have a little delta plus. So this chloride is going to be able to dipole-dipole interact with the carbon that has a chloride ion on it on the next chain over. So we're going to have a little dipole-dipole interaction between these two guys here. It's not a hydrogen bond, so don't say that, but it is a dipole-dipole interaction. So either of those two answers would work according to their rubric. One, this has got more London dispersion forces because it's got bigger electron cloud. Two, this one's going to be stronger because you get dipole-dipole interactions between the chloride and the carbon in adjacent monomers. So not too bad as far as the actual questions they've asked. And like I said, the only other thing I might anticipate is the strength of that. And again, you're going to look at these intermolecular forces, which we've covered, and you're going to look for cross-linking, which would be a giveaway that it is much, much stronger. Okay, so the second subject is mass spectrometry. Spectrometry is not a fun word to say. Go ahead and say it to yourself quietly. Mass spectrometry is a way to sort out particles by mass. So we have a device that you shoot in a sample of some element, you heat it up to vaporize it, you blast it with some electrons, and you're going to knock electrons off of this thing. And we did this before. We knocked electrons off. We looked at a graph that showed the ionization energies of each electron, and you could determine what element it was by how hard it was to knock off these different layers of electrons. I don't know if you remember that, but you could see the S's and the P's and all that stuff. So this is similar to that, but we don't want the electrons this time. Now we want the particle that's left. So we're going to try and knock off one electron, and now we've got a positively charged particle. We're going to accelerate that positively charged particle with an electric field, and then bend it with a magnetic field. And if you think about the inertia of these things, so imagine, let's do a little thought experiment. Imagine I've got a hallway going into a room. And right here, I've got a great big fan. And it blows this way. If I start throwing balls down this hallway, I throw a tennis ball, I throw a bowling ball, I throw a volleyball, I throw a wiffle ball, I throw a ping pong ball. As they come in here, the fan is going to affect them differently. The bowling ball is barely going to move at all, and it's going to hit like here. But the ping pong ball will probably go woo and come way over here. Wiffle ball will be like here. Tennis ball will be out here. Baseball will be mostly here, right? So each one is going to end up in a different place based on its mass. This is exactly what happens in the mass spectrometer. And so down here, we have this detector that is basically like this wall here that determines, oh, a piece hit here, so it must be this big. A piece hit here, it must be this big. A piece hit here, it must be this big. So we can sort them out by size based on where they land. So it's all about the inertia of the particles as they go around this corner. As they're forced around this corner by this magnet, the things that are more massive are not going to turn as much because they have more inertia. So what you often get with a problem like this is a percent mass graph. When you take a sample of any element from nature, it's made up of various isotopes. It's not all, like carbon is not all carbon-12. There's carbon-14, there's carbon-13, different numbers of neutrons. And so they have different masses. And this is what we can sort out with a mass spectrometer. So if I were to draw this graph, it would be like a line like this and a line like this. So the mass that we have on the periodic table, these masses are all in atomic units, and they are based on natural samples. So they include all the normal isotope ratios that we would find. And so if I was just given this graph, I would say, well, what's the thing with the mass really close to 7 but not quite? And I would look through the periodic table, and helium's 4, lithium is 6.94, beryllium is 9.01. I like the lithium, it's just about 7. So almost every mass spectrometry question from AP has one of these graphs. And it almost always just asks, what element is this probably going to be? So let's have a look. This first one here is actually from an AP question. And you can see it's something a little above 90. So you go to your periodic table, find a mass that's a little above 90. And it looks like this is zirconium, because that's 91.22. It's probably not niobium, because niobium is going to have a mass of 92.91, which is way up here. The average mass of this guy is pulled down here by these big ones. So it's going to be somewhere around 91. And that's what zirconium is. How about this one right here? If you haven't been doing this, pause the video and do that one. So if you look at this one, it looks like everything is kind of centered on 96. You can see if you sit at 96, these three seem to add up to roughly about the same amount as those three. And so it's going to be right around 96. And I see that molybdenum, if you look at your periodic table, molybdenum is 95.95, and that is right about 96, so we'll call this one molybdenum. And it just occurred to me that these two are both zirconium. They're the same. Seems like I would have noticed that before I put that graph in there. Anyway, you get the idea. It's not that challenging. Just kind of eyeball it, look at where the middle of all these peaks are. In some cases, you might actually do a calculation with this, but in most cases, it's just what elements this look like, or some question along those lines. All right, so the last subject is that Beer-Lambert law. So we've done spectrophotometry. We did that in the reactions unit. We graphed transmittance, I believe, as some substrate went away. And then we checked to see which one made a straight line. Was it just the concentration over time, the natural log of the concentration over time, or 1 over the concentration over time, to find out if it was 0, first, or second order reaction. But you might get a question like this. So we need to talk about spectrophotometry really quickly, just to remind you. We use a spectrophotometer, which is basically we shine a light either through a crystal or across a diffraction grating, and this allows us to separate it into different wavelengths. We choose a particular wavelength, shoot that through our sample. This is our sample, and then detect how much light is making it through. And we calibrated it with the blank. Remember, we put in a clear solution, shot light through it, and called that 100% transmittance. So because there's going to be some blocked by the tube and the fact that it's the tube full of water. So we just wanted to measure what was blocked by the chemical that was in there. So transmittance is the light that goes through. Absorbance is the amount of light that doesn't go through, gets absorbed by the sample. So an equation that appears in the course description is the Beer-Lambert law. Like I said, they haven't ever used it that I've seen, but it deals with absorbance. This is the way the equation appears on your equation sheet. For some reason in the course description, it looks like this, A equals, and they use this big guy, BC. This is molar absorptivity, but so let me just go through here. This is absorbance, and again, this is something that the spectrophotometer can give you. This is molar absorptivity. And so this is an intrinsic quality of whatever the molecule is. It has a certain amount of ability to absorb that light. Like how intensely does it absorb that wavelength of light? And so it's specific to the wavelength, because some wavelengths will go right through a substance, whereas others will be absorbed. B is just the path length. And so basically that's how far it travels through the sample right here. In most spectrophotometers, that's usually 1 centimeter. And then C is the concentration of the substance. So the kinds of questions you'll get, here's the molar absorptivity. They measured this absorbance. What's the concentration? Or here's the molar absorptivity. It has this concentration. What do you expect the absorbance to be? Maybe less often that one. Or we could say we have a known sample of this concentration. It measured this absorbance. What's the molar absorptivity of this compound? And then you could use that to identify a compound. But this is pretty straightforward. It's 3 numbers multiplied together. And like I said, I don't even have the sample question. It's just going to be, here's all the variables solved for the one that's missing. Like 8th grade algebra, piece of cake. All right, so those are the 3 things that I hadn't covered in class that are in that outline. Like I said, I've got a free response question Friday, and then I'll hit some of those topics that you guys were requested to review on in the next week or 2. Closing in on it here, guys. Stick with it. Keep doing this daily. Don't save it for later. Do it daily. It matters that you do it over a length of time. That's the way learning works. If you do it over a period of time, it's going to be in there better than if you do it all in one go. Love you guys. Hang in there. All right, so the second topic is mass spectrometry. Okay, so the second subject is mass spectrometry. No, spectrometry. 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 Sorry. So mass spectro. So almost every single mass spectrometry with a spectrometer in the mass spectrometer.